All right, welcome back. So as I promised, here's part 2 of our discussion about calculus of parametric curves. The first video we talked about differentiation. This time I want to derive a handful of formulas for involving integration of parametric curves. So let's look at part 2 here. And this will be integration. Okay, and when we're looking at integration, there are 3 formulas I want to derive here. So we're going to derive 3 useful formulas. First one will be area under a parametric curve. So that'll be the first one. The second one is going to be the arc length of a parametric curve. And then lastly, we're going to talk about the formula for finding the surface area of a solid generated by rotating a parametric curve. I'll just say curve because we know by now that it's a parametric curve. So I would like to derive 2 of these formulas. The derivation of the third one is kind of a consequence of the derivation of the second one. So let's start looking. Let's start with area under the curve. And this is how we were introduced to integration back in Calc 1, right? We learned, well, what does the integral of a function represent? Well, it represents the area under a curve of a bounded region. So if we have some curve, say here's our parametric curve over some interval, let me say like A to B here, then how did we find area under the curve? Well, we started by approximating with rectangles. You may remember taking left endpoint and right endpoint approximations in either Calc 1 or Calc 2, or both. And it looked something like this. And again, it was an approximation, right? Maybe I can draw a little more here. You take the sum of all these rectangles, and it gives you an approximation of your area. And so how do we do that? Well, first, we calculate the area of each rectangle. So to do this, we need to know the width, and we need to know the height of each rectangle. Well, to find the width, we need to define an equal partition on our domain. So we have an equal partition of the interval AB. Okay, and so let's take this equal partition to be like, let's say the first number is A, we'll call it T0, and then we'll say that that's strictly less than some T1, strictly less than T2, all the way up to Tn, which we'll call B, okay? Which means we've split this up into n subintervals, right? That's what this equal partition gets us. It gets us in intervals, right? Or subintervals, right? And so what is this first point here, right? This first point on the x-axis is going to be x of t naught, or t0, right? Because that's the first partition in our interval where that t belongs to. So we have x of t0, and then we have like x of t1, all the way up to x of tn. And so then what is the width of one of these rectangles? So let's take, we have this partition here, and we can introduce an index for the subscript here. So let's say that our index is I, and I is ranging from 0 to n, okay? Or how about 1 to n? Well, then the width of the ith rectangle is, well, it's simply going to be x of ti minus x of ti minus 1, right? That gets us this width down here. I'll draw it in green for the ith rectangle. Let's say this is the ith rectangle. Okay, it gets us that distance right there, which we're calling the width of the rectangle. You take the right endpoint and you subtract the left endpoint, and that gets you the distance between the two, right? And so that's this width here. And we also need the height. What about the height? The height of the ith rectangle, maybe I'll call it h in blue, since it's already in blue, right? So we have along the ith rectangle, we need this height. Well, that simply corresponds to this point up here, which is y of whatever point it's over, right? And so to get this height here, we need to pick a point in the middle of the interval, right? Let's say that there's some t value in this interval. Let's say that there's ti tilde such that ti tilde, or excuse me, x of ti tilde is between x of ti minus 1 and x of ti, right? So we're picking a point in this interval that represents the height of this rectangle, okay? And so what that means, to get the height of the rectangle, it's y of whatever point we're looking over. And we're looking over the point x of ti tilde. Okay, so here's our height down here, and here's our width. So the area of the ith rectangle is the product of these two values. So let's say the area for the ith rectangle, we'll denote it a sub I, is height times width, which is y of x of ti tilde times x of ti minus x of ti minus 1, right? And that's the area for one rectangle. We need the area for every rectangle. So the total area, which I'll call A, is approximately the area of the sum of all of these rectangles. So I'll say this is approximately A sub n, which I'm going to denote as the sum from I equals 1 to n of the area of these rectangles, right? X ti tilde, x ti minus x ti minus 1. We can get this into a format that's going to closely resemble a derivative by multiplying the top and the bottom of this sum by our change in t, right? So delta t, we'll say over here, delta t, our change in t is ti minus ti minus 1, right? Ti minus ti minus 1. And so if we multiply the top and bottom of each term by our change in I, we get the sum from 1 to n of y x ti tilde times x ti minus x, sorry, it's minus not product, ti minus 1 over delta t, which is ti minus ti minus 1, and then times delta t, which is ti minus ti minus 1. Well, if you notice, if we took the limit of this piece right here, this is the definition of the derivative of x of t, right? And as you take a limit of a sum, delta t under the limit, delta t goes to dt, right? And so because of this, we can say that A, the area, is equal to, no longer approximated, is the limit as n goes to infinity of an, which is this whole thing right here, this whole piece right here. And if we take that limit, well, then that's the integral from a to b of y of t times x prime of t dt, right? After you take the limit, this piece turns into y of t. This piece in blue turns into x prime of t. And the change in t turns into dt. And we now have a formula for area under a parameterized curve. So let's go theorem. The area under the continuous parameterized curve x of t, x equals x of t, y equals y of t, from t, for t between a and b is given by a equals the integral from a to b of y of t x prime of t dt. So this is how we find area under the curve of a parametric curve, or a curve described by parametric equations. And so now that we've gone through this derivation, and we'll go through plenty of examples in recitation and homework and stuff like that, but now that we've done the derivation, you don't have to go through that messy calculus every single time. You just come to this formula and say, what's y of t, what's x prime of t, what's their product, what's their integral, and you're done. Okay, so that was our derivation of area under the curve. Now let's look at a formula for arc length. Okay, so for arc length now, let's use the same notation for our partition. We're going to need another partition here. We want it to be an equal partition. So let's say here, again, we have like x of t0, x of t1, et cetera, equal subdivisions all the way up to x of tn. Okay. And now we want the arc length of this curve. We can approximate arc length by taking lengths of line segments here. So this curve, we've now partitioned n times. And to get an approximation for arc length, we can take line segments between the endpoints of our partition, because we can find a formula for the line, or for linear distance between 2 points, right? Remember the distance formula, like way back in high school geometry even. We can use that multiple times to get a formula for distance of line segments, which will give us an approximation of the arc length of the curve once you sum up all the distances of these line segments here. So we can find distance of the ith line segment we'll denote it as d sub I, and the distance formula tells you you take the difference of the x coordinate, and so in this case it's going to be x ti minus x ti minus 1 squared plus, and then the difference in the y coordinates squared. So we'll have y of ti minus y ti minus 1 squared. And this gives us the distance of the ith line segment. Say this is the ith line segment up here. Okay, and so again, now we know that arc length, which will be lowercase s, because later surface area will be denoted by uppercase S. I can try to make this even smaller. There we go. So arc length is approximately the sum from I equals 1 to n of our line segments, which was x of ti minus x of ti minus 1 quantity squared plus yti minus yti minus 1 quantity squared, close off the square root, right? So this is approximately arc length. Now we want to be able to, again, as we did with a formula for area under the curve, we want to be able to pass this to a limit. So it becomes not an approximation, but an exact value. So to do that, we need to, again, introduce a change in t, like a delta t, because we need to start seeing derivatives and dt's and delta t's coming up and stuff like that. So before I do that, we first need to recall a theorem from Calc 1. Let's recall the mean value theorem. The mean value theorem, I could draw a picture with it here. So let's say we have, here's A, here's B. This is some curve, y equals f of x. And let's say there's some point in between A and B, we'll call it C, okay? The mean value theorem states that, let's let f of x be differentiable on the open interval a to b. We require, I won't write it, but we require that it's continuous on the closed interval a to b. It needs to be differentiable on the open interval a to b. Then there exists some value c between a and b that I indicated over here, such that f prime of c is equal to f of b minus f of a over b minus a. So what it's saying is somewhere between points A and B, there is some point C in here such that the derivative or the slope of the tangent line at that point is equal to the mean value across this interval, right? It's f of b minus f of a over the length of the interval, hence the mean value theorem, right? Another way that we write this and how I'm going to use it in deriving the integration formula for arc length is, and we'll see it in this format, and it's to say that f prime of c times b minus a equals f of b minus f of a. Okay, so this was a quick recollection of the mean value theorem, and in particular, I wanted to remind us of the mean value theorem expressed in this way, because I'll be using it in our context. So what does the mean value theorem get us in this case? By the mean value theorem, there exists, I'll call them Ti star and Ti tilde, such that x of Ti minus x of Ti minus 1 is equal to x prime of Ti star delta t. This is exactly the mean value theorem. Instead of A's, B's, C's, and F's, I'm using Ti, Ti minus 1, Ti star, and X, right? So it looks a little more intimidating in this form, but I promise you this is just the mean value theorem, right? And this also, again, by the mean value theorem, we know there exists this Ti star such that it fits into the mean value theorem in this way. And then also that y of Ti minus y of Ti minus 1 is equal to y prime of Ti tilde delta t. So here I had to use the mean value theorem once for the function x, right? So like here we'll have some x is a function of t. Somewhere we have x sub I minus 1. Somewhere we have x sub I. Sorry, t, my bad. T sub I. Somewhere we have t sub I minus 1. Somewhere in the middle we have t I star. And then I'm using the same argument as the mean value theorem to say that there exists some Ti star between these two values such that I get this formula. And I can do the same thing for the function y of t and get the same thing, but with Ti tilde instead. And so why do we want to use those? Or why do I need the mean value theorem here? The reason is because now I can replace these in our formula. If you remember, S was approximately the sum from I equals 1 to n square root of x of Ti minus x of Ti minus 1 quantity squared plus y of Ti minus y of Ti minus 1 quantity squared, right? This was our approximation. We took the sum of line segment lengths and saying, like, that's pretty close to the area or the arc length for the curve, but it's not quite because our curve isn't non-continuous line segments, right? It's one continuous curve here, so this is only an approximation. But by the mean value theorem and the introduction of this Ti star and Ti tilde, I can say, well, this is the sum from I equals 1 to n of x prime Ti star squared plus y prime Ti tilde squared. Forgetting my dt's here. Let me fix that. x prime ti star delta t squared, right? Because using this formula here, and then I'm going to use it again here, plus y prime ti star dt squared. Now, if I square these and I can pull out the common delta t here, I can actually cancel the square root with the delta t squared and just have a delta t on the outside of the square root. So if I do that, I'll get sum from I equals 1, so I'm running out of room, I equals 1 to n of square root x prime ti star squared plus y prime ti tilde squared. And now I have a delta t on the outside. And once I'm here, I want to take the limit to translate this from an approximation to the exact value. So then arc length S is going to be the limit as n goes to infinity of, so let's see, let me call this entire thing here, which is the same as this entire thing at the bottom, let me call this S sub n, right? Because it's the sum from I equals 1 to n. And then I want to take the limit as n goes to infinity. So we're getting smaller and smaller and smaller intervals, more and more and more segments, etc. So I want the limit as n goes to infinity of S sub n. If I take this limit, I then get the limit as n goes to infinity of sum from I equals 1 to n x prime ti star squared plus y prime ti tilde squared delta t. This limit then becomes the integral from a to b of x prime of t squared plus y prime of t squared dt. And so this is the theorem. Theorem is that for a parametric curve, this is arc length, is given by this formula. So to find arc length, you don't have to go through this really rigorous derivation of the arc length integral. You just look at your parametric curves, you take the derivative of x, take the derivative of y, plug them into the formula and integrate. And we get this nice formula for arc length. Okay. And to wrap this up here, I promised that I would also talk about surface area given by a parametric curve. So we say we have some parametric curve. Say it does something like this from A to B. Well, we can rotate. You can imagine rotating this curve about the x-axis. Kind of taking this, imagine taking a string and wrapping it around. And you see what this solid would give you. We get something like this here. If we rotate this around the x-axis, we get something like this, where this is a three-dimensional shape here, and this in red is kind of the front. And then, you know, you can imagine this goes around to the back side, and then it's like a warped Pringles can or something. And we can directly derive the formula for surface area based on what we just knew about arc length, right? So arc length gets us the length of the side of this thing. The height, right? If we were to cut this up into a slice, one of these circles in here would have a radius of y of t, right? And so what's the area of a circle, right? The area of a circle is, the circumference. We want the circumference of this circle, right? What's the circumference of that circle in there? The circumference is 2 pi r. But we know that r is y of t, right? R is y of t because as you change your position in the x-axis, the height of the circle is going to change, right? So the circumference is going to change. And so we have 2 pi times y of t, right? But then we need that times the length of this solid, but we know what the length of the solid is. It was the integral we just had, right? So that means the integral for surface area is going to be 2 pi r, right? Integral a to b. I'm going to write the r inside the integral, right? First off, it would all be in the integral. I can pull out the 2 pi, right? So basically, the surface area is found by taking the circumference of these circles times the length of the solid, right? The circumference is given by 2 pi r, which is 2 pi times y of t, times the length of the solid. And the length of the solid was given by the arc length of the parametric curve that we started with. So that means the formula for surface area is 2 pi integral from a to b of y of t times x prime of t squared plus y prime of t squared dt. And there's our formula for surface area. And so now we can use all of these to our advantage when calculating or when trying to do calculus with parametric curves. And again, we'll see plenty of examples in the homework and recitation. And this wraps up the lecture for the derivation of these formulas. So I'll see you guys in the next video.